Hello everybody, in this lecture we will be solving 1996 IMO problem number 4. Here's a view of this problem. The positive integers a and b are such that the numbers 15a plus 16b and 16a minus 15b are both squares of positive integers. That's important. So the hypothesis tells us that 15a plus 16b is equal to u squared, and similarly 16a minus 15b is equal to, say, v squared, where u and v are both greater than or equal to 1. Now the trick of the problem, kind of like the crux move, is to consider the following expression: u to the power 4 plus v to the power 4. Well, that's simply u square plus v square, and that's equal to 15a plus 16b squared plus 16a minus 15b squared, and expanding and rearranging, I guess, 225a squared plus 2 times 15a times 16b plus 256b squared plus 256b squared minus 2 times 16a times 15b plus 225b squared. So these two would cancel out, and I have some interesting terms which look very similar. Hold on. No, this thing is an A here. Sorry for that. That one is an A. Sorry. Okay, so if I combine these, I realize that this is 225 plus 256 a squared plus the same numbers, 225 plus 256 b squared, but 225 plus 256 is 481, so therefore I have 481 and the a squared plus b squared following them. But then 481 is simply 13 times 37, and I have a squared plus b squared. Now I come to an important point. I just realized that u to the 4th power plus v to the 4th power, sorry for that, is divisible by both 13 and 37. So this would imply that u to the 4, in modular arithmetic notation, that simply means this is congruent to 0 mod 13, and u to the 4 plus v to the 4 is also divisible by 37. Okay, but then looking at these expressions, we can conclude that what this condition means, for instance, if you focus on this condition, it means that either u and v, either u, v are both equal to 0, or u, v are both not equal to 0, right? And in a similar way for this one, so either u, v are both equal to 0, or okay, so for that, when I say equal, I mean congruent, right? So equal here, so they are either both congruent to 0 or they are both not congruent to 0, so such in mod 13 and in mod 37 respectively. So therefore, to write it in plain English, so either u, v both sorry for that, divisible by 13, or u, v both not divisible by 13. And similar way for the other one, so the expression here is either u, v both are divisible by 37, or u, v both not divisible by 37. But which one? It turns out that both of them are at the same time divisible by 13, and both of them are divisible by 37 at the same time. The trick is to consider the following algebraic identities. So first consider this one. u to the 12th power plus v to the 12th power, which we can factorize as u to the 4th power plus v to the 4th power times u to the 8th power minus u to the 4 v to the 4 plus v to the 8th power. And in a similar way, I can go ahead and have a look at u to the 36th power plus v to the 36th power, which is simply equal to u to the 12 plus v to the 12, the sum of cubes here. Just think of it like that. U to the 24 minus u to the 12 times v to the 12 plus v to the 24, if I'm not mistaken. Okay, so this would imply, therefore, that, for instance, in mod 13, we know that u to the 4 plus v to the 4 is 0, right, from this condition. So therefore implies that in mod 13, u to the 12 plus v to the 12 is congruent to 0 mod 13. But in a similar way, if you consider the second expression here, for instance this one, and consider it in say mod 37, u to the 36 plus v to the 36, I claim is congruent to 0 as well in mod 37, and it's because well, it's because of the following fact: u to the 4 plus v to the 4 in mod 37 is 0, and then that means this guy is 0 in mod 37, but that guy is 0, meaning this guy must be 0 in mod 37. Okay, so let's focus on the first side, the left hand side. So if u and v, so let's first consider the alternative. If u and v are both not divisible by 13, what it implies is that if you apply Fermat's Little theorem, so 13 is a prime, 13 minus 1, 12. So by Fermat's Little theorem, u to the 12 is congruent to 1, and v to the 12 again is congruent to 1 in mod 13. But this implies that u to the 12 plus v to the 12 is congruent to 2, not 0 in mod 13, which can't be. So therefore, let's go on. Therefore, u and v are both congruent to 0 mod 13, so they are both divisible by 13. And if you apply a similar argument for the for this expression, again let's assume again to the contrary that u and v both not divisible by 37. So as a result, by again Fermat's Little theorem, I know that u to the 36, and because 37 is a prime, so p minus 1 here. Okay, so this is congruent to 1, and v to the 36 is also congruent to 1 mod 37. But then it implies that u to the 36 plus v to the 36 is congruent to 2 and not 0 mod 37, which is a contradiction here, obviously, right? So therefore, u, v, they are both congruent to 0 mod 37 as well. So they are both divisible by 37. So now we can say, so this implies that u and v, they are both divisible by 13. So u, v both divisible by 13 and 37, implying that u and v, u and v are divisible, both divisible by 13 times 37. But then their squares, u square and v square, they are both divisible by well, 13 times 37 we earlier established is 481, so 481 squared, suggesting that the minimum value, so that we are actually seeking, that u square and v square can take is greater than or equal to 481 squared. So is this attainable? Basically, that's the question. And sure enough, if you consider, for instance, the case where u and v, they are both equal to 481, the minimum value, let's see if it is attainable, and you plug it into our initial equations, namely 15a plus 16b, 15a plus 16b is equal to 481 squared, and the other one, namely sorry for that, 16a minus 15b. 16a minus 15b is equal to, again, 481 squared. Remember, this one was u squared and this one was v squared. Then we have a system of equations for a and b, and in fact, if you solve this system of equations, you would get that a is equal to 481 times 31 and b is equal to 481. So you get legitimate answers for well, positive integer values for a and b, which implies that therefore 481 square is actually the minimum value that we needed to find. So the least possible value that can be taken by the smaller of these two squares is 481 square. And we are done. Hope to see you in our next video.